All right, so in this lecture, we're going to be reviewing quantum numbers. Quantum numbers are hard for most students because quantum numbers require pretty much that you understand that electrons are localized into certain probability distributions. So we talked about quantum mechanics, and quantum mechanics governs the world of the very small. And out of these quantum mechanical calculations, we discovered probability distributions of electrons. So electrons aren't just localized to one area. We can't pick out an electron and say it'll be there in an atom or there in an atom because of Heisenberg's uncertainty principle. But we can state to a very definitive certainty where the most probable location of an electron is. So we can state, hey, the electron will be around the atom in this area at any point in time, or this area at another certain point in time. But different electrons are found in different places. So we have to come up with a bookkeeping method of where this electron is most likely to be at any point in time. And that's why we get orbitals. So orbitals are probability distributions. And when we look at an atom, we say, okay, where is this electron? Well, that electron is in the s orbital. So 99% of the time it will be in a spherical coordinate system where we can find it in this sphere about the atom's nucleus. Now, where it is governed by the quantum numbers of any given electron. So let's start with an electron in a ground state of, let's say, hydrogen and helium. Well, hydrogen and helium have 1 and 2 protons respectively, which means in a neutral atom in its ground state, in its unexcited state, it has 1 and 2 electrons. So let's start off with 1 and 2 electrons. Well, what's the ground state of the atoms anywhere? Well, the first state is the first principal quantum number, which is n equal to 1. So if n is equal to 1, your first principal energy level is here. So you're at the first principal energy level. Now you can go up to any integer amount from n equal to 1 to n equal to infinity. Those are the energy levels allowable as a quantum number. So then from this principal energy level, what this means is that we are at a certain distance from the nucleus. So right here I've drawn a coordinate system, and I'm going to put my nucleus right there. That's my nucleus of my atom. Now when n equal to 1 is a given certain distance away from the nucleus, right? So you can think of the principal energy level like the president of the school, right? It's the governing body. The school can only go as far as the president. But the president doesn't do much, right? I mean, they run things, but they don't physically tell you anything about the system. So an n equal to 1 is the governing body, right? It tells you the distance you can be. So an n equal to 1 is the closest distance you can be to the nucleus. So then let's look at the angular momentum quantum number. The angular momentum quantum number has allowed values. You can have 0 through n minus 1. Now what that means for a value of n equal to 1, your allowed L values are 0 through n minus 1. Well, what's 1 minus 1? Well, that's 0. So your only allowable L value is equal to 0. Well, what does that mean? What is the physical interpretation of an L equal to 1? Well, this is like the curriculum coordinator underneath the president, right? And n equal to 1 is the president. That means that you can go only this distance from the nucleus. An L value equal to 0 gives us more information. Now we know that an L value of 0 is a spherical looking orbital. It looks like a sphere. What that means is that at any given time in this atom, I can find this electron located in a sphere about the nucleus in a three-dimensional world. Now this is a sphere. Remind yourself constantly that this is a sphere. So it's three-dimensional. It's not one-dimensional. It has sides on all. It has all sides. So then now this L equal to 0 physically interprets that it is in a sphere, which means that 99% of the time I will find an electron in that energy level. Now we call the L equal to 0 subshell. We call this our S subshell. Now, constantly I get the question, why S? Well, it's it comes from a German word. Why AU for gold? Well, that's because historically gold was called Aura. So then we symbolize that as AU. Does it make sense nowadays? No, not at all. Does an L value of 0 comprehend to us as S? No. But we have to memorize it, and we have to say L equal to 0. That's the sphere. That's that general shape. Now it can change, right? Now let's move up a step, and then we'll come back to this. Let's move up a step to n equal to 2. Right? If my n equals 2, now my allowable values are 0 through n minus 1. Which means I have 2 allowed L values. I have an L value equal to 0 and an L value equal to 1. Well, my L value, again, corresponds to an S subshell. And that L value subshell gives me a spherical-looking orbital, spherical-shaped orbital. So then now I have an orbital that looks like this. Now, this is a very simplistic view of this. But the only difference between a 1s orbital and a 2s orbital is number 1, its energy level, and number 2, its distance from the nucleus. Now, they do have nodal planes, and they do have absences of electrons in certain areas, and that does change according to the quantum number, but we're not going to go into that. You'll go into that in college. So now I have a 2s subshell. It has the same general shape. It has a spherical shape. Same s subshell, different energy level. Now that's angular momentum quantum number. The next quantum number that you have to look at is the magnetic quantum number. The allowed values for the magnetic quantum number are anything from negative L through positive L. Now what that means is if my L value is 0, my only allowable values are 0, negative 0 through positive 0. So my only allowed value is 0. So my M is equal to 0. Now the magnetic quantum number gives me my general orientation in space. So what this means is an M equal to 0 means that you have one physical orientation. A sphere is a sphere. If it's sitting in 3D space, my sphere looks like this. If I rotate it, still a sphere. I have a sphere right here. Now if you look at this ball, it's a sphere. If I rotate it this way, it doesn't change its orientation in 3D space. I can spin it all I want, and it doesn't face or favor any axis. That means that it has one physical orientation. So now that means that my S subshell has only one orbital. Now that's a designation that we're going to make. So then now we have one physical orbital in the 1s subshell. That makes sense? Because we only have one M value, which means we have one orientation. So we have one physical orbital. Now my S, my spin state, has only allowable values of positive 1/2 or negative 1/2. Which means that in an M value of 0 or an M value of any integer, then we only have allowed values of positive and negative 1/2. So my S is equal to positive 1/2 or negative 1/2. Now, what does that mean? Well, an electron spins in its orbit, and its spin gives its angular momentum, but its spin, its velocity and its travel around the nucleus gives its angular momentum, but while it's traveling around the nucleus, it's spinning like this as it's traveling, right? And we have to track that spin, because if two electrons are in the same orbital, they want to have opposing spins so that they can exist. If we have two negative charges, they want to repel. But if we give them two opposite spins, they can exist in the same orbital. So in my 1s orbital, I can contain two electrons, one with a positive 1/2 spin and one with a negative 1/2 spin. So now what does this look like as a physical identity on paper? Well, when we're doing problems, we're gonna take this up as the first principal energy level. L equal to 0 gives me an S sublevel, and then my M gives me one physical interpretation. So I'm going to draw 1s space. That space gives me the ability to input my electrons. Now when I'm filling my 1s orbital, I fill one at a time with opposing spins. So an electron is signified by an up arrow. And the opposing spin of negative 1/2 is signified by another arrow. You'll see them with a full head and a half head. I draw mine with a half head. So then now when we look at this orbital, this is how we're going to say this is our orbital designation. Now this is going to become important in orbital notation. So when we look at this, okay, so we have an n equal to 1, L equal to 0, m. This can't be this easy. This isn't the only thing. It's not. That's not the only thing. As soon as we get to upper echelons of the L value, we introduce new orbitals. So with an n equal to 2, we have allowed L values of 0 and 1. Here, again, we have our S subshell. We have our S subshell. But instead of being our 1s, because we're going to designate this the 1s orbital, now instead of the 1s, we have the 2s. The 2 coming from the principal energy level, and then my s coming from my L value. Now, instead of s, an L value of 1 corresponds to the 2p subshell. Notice that the p orbital does not exist in the first principal energy level. Well, that means that as you have to get further out from the nucleus for the p orbital of that probability location to exist. So then we have the 2s orbital and the 2p orbital. Now, with an L value equal to 0, you can only have one allowable m value, and that's 0. But with an L value of 1, you have 3 allowed m values. Our allowed m values are m equal to -1, m equal to 0, and m equal to 1. Well, look up here. So my magnetic quantum number is -L through +L. It can be any integer in between going through 0. So if you notice, I have an L equal to 1, I have -1, 0, and 1. Now within those magnetic quantum numbers, I have 2 allowable spin states. I have positive and -1/2. Now how does this function in 3D space? Well, I'll tell you how it functions. A p orbital looks like a dumbbell. So the probability distribution for my electron in a p orbital looks like this. So it does like a little race car track thing. But now it doesn't enter into the nucleus. It goes around it through what's called a node. And it orbits the nucleus like this. Now if I look at the p orbital, I have a 99% chance of finding the electron inside that location. What does this look like in 3D space? Well, it looks just like this. It looks like a dumbbell. So we draw it like that. Now that is my p orbital. Now it changes. I have 3 p orbitals. Now how does that exist? Well, I have 3 different orientations. Remember, the magnetic quantum number describes the orientation, and because we had a sphere, it only had one orientation. But now that we have a dumbbell, now when I change the dumbbell, it changes its physical orientation. So now when I look at this, I have this orientation, or I can turn it 90 degrees and I can have this orientation. Or I can turn it another 90 degrees, but this way, and have it facing at you like this. So it has 3 specific orientations. So then that means that not only is it just vertical up and down, but we can have a p orbital orientation here through the x-axis. We can also have a p orbital orientation here through the y-axis. Now what does this do for us? Well, this means that because I have 3 separate orientations, now I can put 2 electrons in each orbital. So instead of just having one orbital as my s subshell, now with the p orbital I can have 2 electrons per p orbital. So I have a px, a py, and a pz. So then now this is going to be my px, my 2py, and my 2pz. Now, the orientation designations will become important later on in life, but right now they're not super important. Just try to keep them straight. Make sure that you understand that a p orbital exists on one axis, and we designate that axis underneath the p orbital. But assigning it to a specific m value won't really matter right now. So the 2px, the 2py, and the 2pz each have allowed spin states of positive and -1/2. So now in each orbital, I can stuff 2 electrons. So then now in my 2p sublevel, I can have a total of 6 electrons. 2 in 2px, 2 in 2py, and 2 and 2pz. But I can also have 2 electrons in my 2s orbital, which means I have a total of 8 allowed electrons in my second principal energy level, right? So I have 2 allowed electrons in my first principal energy level, and now I have 8 electrons in my second principal energy level. Now you got to be asking yourself, well, that's really cool, because in the first period, I have 2 elements. Well, what happens in the first period? Well, your first energy level is filled in the first period. So hydrogen and helium occupy the 1s orbital. So does that follow for the second period? Well, yes, it does. In the second period, you fill the 2s orbital, which is filled by lithium and beryllium. So lithium and beryllium fill the 2s orbitals. And then once you move on to the nonmetals, you start to fill the p orbitals. Does that have an effect on its chemistry? Yes, it does, and that's what we'll learn about in Chapter 5. But right now, how do we fill these orbitals? Well, we have orbital designations here, right? So then now, what we're going to learn in our next lecture is how to come up with orbital designations and then fill that for orbital notation. And it follows directly from quantum numbers. So you always have to keep in mind that these orbital designations follow directly from the quantum numbers. So we can't just forget about them and say, well, that was a curious, quirky side thing that we talked about. No, the quantum numbers form the basis for orbital notation and then chemical bonding. Because what we're going to see is a half-filled p orbital is most likely going to form a bond with a half-filled p orbital. Or we can hybridize s and p orbitals into an sp orbital and then bond with a p orbital. So we're going to have all these funky things, but it follows directly out of my quantum numbers. The reason being is because of the simple allowed rules for assigning quantum numbers.